In this video, I will talk about the chemical equilibrium, and at the end of the video, you will understand this important concept. And if you know the concept, you can go on the examples. At the end of the video, you can see the examples. And we can start. So consider a reaction. This is a reaction. And for this reaction, as you see, there's a double arrow. So this means that there is a back and forward reactions. This is a forward reaction and this is the back reaction. So there is equilibrium between A, B and C and D. And this kind of reactions, calculating concentrations is not easy. It is not straightforward. And before going to concentration calculation, we have to mention something which is called as equilibrium expression, which is called as Kc. And for this reaction, Kc is equal to C to the power C, D to the power D, and A to the power A, and B to the power B. If the Kc is bigger than 1, it means that numerator is bigger, so reactions goes to the product side. If Kc is equal to 0, then reaction is at the equilibrium. No. If Kc equals to 1, it means that reaction at equilibrium. And if Kc is smaller than 1, then denominator is bigger, which means that reactions goes to the reactant side. So these are the products, right? And these are the reactants. And there is another important thing. Kc can include only gases and aqueous species. So for instance, you can write the liquids or solids. You can't write them into the equilibrium expression. And for instance, how can we calculate the concentrations? For instance, we have this kind of reaction. This is a very common reaction that is used in the books. And for instance, you have 1 mole PCl5 at the beginning, and there is 0 amount of PCl3 and Cl2 gases. Okay, and what will be changed after reaction happens? So firstly, PCl5 decreases, let's say minus X. If it is drops about minus X, then PCl3 increases plus X and Cl2 increases as plus X. And at equilibrium, I will add them up. 1 minus X plus X plus X. And this reaction has a equilibrium constant. And we can write the equilibrium constant for this reaction. And it will be, so X, they are plus already, X time 1 minus X. And we can calculate the concentration by finding X if we know the Kc value. And if the reaction is not at equilibrium, we write the same equilibrium constant, but we name it as Q. Again, we have this kind of reaction. And we want to write a value, an equilibrium constant. If it is not at the equilibrium, or we have a suspicious, then we write the same expression. However, in this case, Q might be smaller than K, or Q can be bigger than K, right? If the Q equals to K, then it means that reaction is at equilibrium. But if it is not the case, if the Q is bigger than the K, then the reaction goes to the reactants. And if the Q is smaller than the K, it means that reaction goes to the products. So it is just a basic math, right? It is easy to understand. And there is another expression for the equilibrium, and it is for the homogeneous equilibrium. So all the reactants or the species are in the same phase. All species are in the same phase. So what does it mean? I want to give an example. For instance, this N2O4 gas back and forth reaction to NO2 gas phase. So we can write the Kc for this reaction, right? And Kc becomes NO2 concentration square over N2O4. And for this kind of reactions, if all the products is in the gas phase, then we can use the pressure. Since gases have pressure, right? And if we want to use the pressure, then we can write a Kp. And Kp for this kind of reaction, so I will keep it simple in this case. For this kind of reaction, it is gas of the B and power B and gas of A power A. So it is the same thing with the Kc, but I use pressure, right? So it is easy. And there is a relation between the Kp and Kc. This is very important and it is always be asked in the exam. Kp is equal to Kc times RT delta N. What is delta N? Delta N is B minus A. So I am still considering this reaction. So you have to memorize it. It is very important. So delta N here, mole of the gaseous species for the products minus moles of the gaseous reactants. Or I can write it delta N equals to moles of gaseous species minus moles of gaseous reactants. So this is important. And I want to make some examples. So examples are important for us. So write equilibrium expressions for the reactions Kp and Kc. So if we look at the first reaction, A, we can write the Kc, which will be H3O plus concentration times F minus and half nu. Not half nu, HF. So as you see, water is in the liquid phase, and I cannot write water here. I cannot write water. And for the similar thing can be done for the B. So B, I want to write the Kc, NO2 gas square NO square times oxygen. As you see, all of them in the gas phase, therefore I can write Kp for this reaction. In A, there is no gaseous species, and I cannot use the Kp. So in the B, I can write Kp, and it is P of NO2 square P times NO square and pressure of the oxygen, and this is the Kp value of this reaction. In second example, the equilibrium constant for Kp for the reaction is 158, and calculate the PO2. And PNO2 pressure is 0.4 and PNO pressure is 0.270 atm. And we have to calculate the numbers, but first I want to write the Kp. So Kp for this reaction is PO2 times PNO square over PNO2 square, and this number is equal to 158. So I will put the numbers. I will put this number here, and I will put the not here. I will put this number here, and I will put this number here. So oxygen pressure times PNO pressure 0.270 square over 0.4 square equal to 158. So 158 times 0.4 square over 0.270 square should be equal to PO2 pressure. What I did, I put this number here, and it goes to the denominator side, and I can find the PO2. So let's calculate the number. 158 times 0.4 times 0.4 equals to 25. 25.28 over 0.27 times 0.27 equal to 0.0729, and this is equal PO2 and what is the unit? Unit is ATM. So never forget to write unit, since the unit in the questions is given as ATM. So third example, for the reaction N2 gas plus 3 hydrogen gas becomes 2 ammonia. So this is back and forward reaction. Kp value is 4.3 times 10 to the minus 4 at 375 Celsius, and calculate Kc. So we know that Kp equals to Kc times RT delta N. So delta N is 2 minus 3 minus 1, so it should be minus 2. And Kc value is asked. We know the Kp value. And I will write the Kp value. It equals to Kc times RT. R value is 0.0821. By the way, it's a constant. A gas constant here. Temperature is not 375. We have to convert it to the Kelvin. To do that, I will sum with 273, and it is 648 Kelvin. I will write this number to the temperature side, and delta N was minus 2, right? Delta N is equals to 2 minus 2 is here, minus 3 comes from here, and minus 1, so it's minus 2. And I want to calculate these numbers, and I will use a calculator. Oh, and I will calculate Kc, right? I don't want to make a mistake. Kc should be equal 0.0821 times 648 minus 2. So this part goes to the here, and Kc should be equal to this value. And now I can calculate it. 4.3 times 10 to the minus 4 divided by 0.0821 times 6 to 648 and it becomes 1.217.